Welcome to note set number 5, where we'll be talking about some basic properties of systems, regardless of what kind they are. Continuous time, discrete time, physically electrical, physically mechanical, whatever. That's one of the beauties of this theoretical view is we can learn the things that are common across all the different disciplines, and then if we're suddenly forced with working in a different area, we've got the basics already down. So some basic ideas here. Again, like I said, fundamental properties. And by understanding these fundamental properties, we get a pretty powerful set of tools. So here's the three main fundamental properties that we're going to study: causality, linearity, and time invariance. So we'll talk about each of those in turn. So a causal system, also called a non-anticipatory system, you can see why we settle on causal instead, basically says that the output at some time, say t1, whoops, I gotta reset my pen here. The output of a system at t1 does not depend on any values of the input that are in the future of t1. Now, that's a simple definition, and to put it in like a fortune cookie kind of format, we can say the future input cannot impact the now output. So that's one way to think about it, and it's a little bit of a rough non-mathematical way, but it captures the essence pretty well. If we have no stored energy in our system, a causal system can't have a non-zero output until we apply some non-zero input. So in other words, if the system is just sitting there with no energy in it, it's sitting there static, not moving, it's effectively at zero, its output is zero, we can't suddenly have it start to respond to this input, to some input, before the input goes from zero itself. That kind of makes sense. So that gives us a visual way of thinking about this. Again, remember this is zero initial conditions. So here is a causal system. The input goes non-zero at that time, and the output stays zero until that time and then starts to respond. Now, it could respond later. It doesn't have to respond right away, but what it can't do is respond ahead of time. So it can't do something like that. That would be non-causal. How does the system know to start responding there before the input actually happens? How do you know? How could you possibly start working on homework assignments before I actually give them? You can't. You're a causal system. So that's the basic idea. So the vast majority, in fact, I venture to say every system in nature is causal. I hedged my bets here, most systems, because physicists keep coming up with weird and wacky things like God particles and things like that. So just in case, I hedged my bets here and said most, but really every system that you're ever going to encounter, at least in my lifetime, is highly likely to be a causal system. Okay, good. So that's causality. Linearity simply means that the system allows superposition to hold. So stated mathematically, suppose we have a linear system and we put in some input called x1 and we label the thing that comes out y1. Okay, good. Now we're going to take that same system and we're going to put in some other signal, x2, and label the thing that comes out y2. If the system is linear, then we can create some new input, which is just a linear combination, some coefficients times each individual previous input, add those together. That input must, if the system is linear, create an output that is the same linear combination of those two outputs. That's it. Now, it's not enough to show that this holds for some x1 and some x2 and some a1 and some a2. No, this has to hold for any possible combination of those, or another way to say it, for every possible combination of those. So that's the idea. So for nonlinear, However, to show something is nonlinear, all we need to do is come up with one counterexample. Here's an x1 with its corresponding output. Here's an x2 with its corresponding output. And if I do a linear combination of those two inputs, I do not get a linear combination of the two outputs. So that's the distinction between a linear and a nonlinear system. So linear systems allow us to take some complicated signal and break it down into parts and figure out how each part goes through, just like we did in that example in the last video where we had some complicated pulse function and we broke it down into just a bunch of shifted unit steps. And that helped us analyze the response. So if a system is linear, sort of a special case of that superposition is if I have some signal x of t and I get a y of t from that, if I put in some scalar multiple, k times x of t, where k is just some scaling factor, the output that I originally had also gets scaled. So I double x of t, I have to double y of t. That will hold for any linear system. So as I said, this idea of being able to use superposition to analyze a linear system, whether there's physically multiple sources or not, is a lifesaver. It allows us to take some complicated input signal and decompose it into an imagined sum of simpler signals, and that's the whole point of what we do. And a lot, I hazard to say, 95% of what we do in this course, maybe even more, basically boils down to decomposing arbitrary signals into things that are simpler. And we'll be talking about Fourier transforms and Laplace transforms, and basically all of those correspond to things called frequency domain methods. And the essence of frequency domain, to simplify it a little bit, is to take any desirable complicated signal, break it down into the sum of sinusoids or things pretty close to sinusoids. And it turns out, as you should probably already know from circuits, it's really easy to figure out how a sinusoid goes through a circuit. And we'll see that it's very easy to figure out how a sinusoid goes through a linear system as well. So in the real world, if you see something that's made up of only R's, L's, and C's, it's a linear system. Once you start putting in diodes, transistors, op amps, then you have the potential to be nonlinear. But someone could have designed that circuit, even though it has all those active components, diodes, transistors, op amps, all the semiconductor type stuff. You could design it so that it's at pretty close to linear, or is exactly linear, at least over a certain range of input values. So like a high quality audio amplifier should be very linear. However, a good guitar amp, at least for rock and blues, generally is desired to not be linear. So anyway, we're going to focus on linear systems because those are the easier ones to analyze. The third property, we've had causality, we've had linearity. Third property is called time invariance. And basically this just means that the structure of your system, how it behaves, how it works, its inner workings, aren't changing over time. So you've got some RLC circuit. The resistor value, inductance value, capacitance value is fixed. They are not varying with time. Their values are time invariant. Then the system itself is time invariant. So another way to think about it, though, a more technical view, is we say that a system is time invariant if we apply some signal, say x of t, and we get some output y of t. Now the next step is to move the x of t to start at some other time. So now we're moving it from starting at 0 to starting at t0. So we've shifted the input. If the system is time invariant, then the output does nothing more than just shifts the same amount. Now, again, just like for linearity, it's not enough to show that this holds for some specific input and for some specific amount of shift. You have to show that it holds true for any input with any amount of shift. Mathematically, it's pretty hard to prove this, but for the most part, we can look at our physical systems and say, okay, I'm not going to tweak that resistor. I'm not going to sit there and change that as time goes on. Therefore, my system should be time invariant. So for the continuous time world, we've seen that things are described by differential equations, and we would like our systems to be linear and time invariant, which we will call together LTI, linear time invariant systems. So remember that abbreviation, LTI. And so the types of differential equations that we're interested in that are LTI look like this. And this is a pretty small subclass. You saw some differential equations unlike this in your differential equations class, but these are the most straightforward ones. We just have a bunch of derivatives of the output as well as derivatives of the input. The dot dot dots allow us to write this down in an arbitrary order kind of way. So this notation just means the nth order derivative. The other thing here is that these coefficients, in front of each term we have a coefficient. Same thing over here in front of each term. So each term is just a different order of derivative, and there's a constant coefficient out in front. So if it looks like this, it's linear time invariant. Now that's not to say that this handles all LTI systems, but this is a pretty good subclass that we'll limit ourselves to. Now, there are to check for nonlinear terms, if you have anything that looks like this, you have your input or your output raised to the nth power, or different orders of derivative of the input times each other, or any nonlinear function like a sine or square root of the input or output. None of those things can be allowed. But bottom line, look for this form. If you see that form exactly and can match it up term by term for some arbitrary n and some arbitrary m, then you're good to go. Same thing for difference equations. It's except here, instead of having derivatives, it's just different shifted amounts of the input. Again, the coefficients have to be constant in order to be time invariant, and we can have no nonlinear terms. So in a similar kind of way, no powers, no cross products. You can't have an x times a y, no square roots involved or anything like that. So to summarize what we've seen in this video lecture, we're looking at systems, whether they're discrete time or continuous time, and we're looking at a subcategory of systems that are both linear and time invariant, and we call those LTI systems, linear time invariant systems. And even though we will focus mostly on causal systems, because that's what we'll see in the real world, as we go through the theory, occasionally we'll be wishfully thinking, gosh, I'd like to have a system that does this. And then we analyze it and discover, can't. It's a non-causal system. And since we can't have a physically realizable, real-world, non-causal system, that's an important thing to see. We go, oh, crap, I can't have what I really want. Doesn't that happen often? Too often in the real world? Yeah, but that's what makes us want to be engineers. We try to get the best that we can within the constraints of the real world. Okay, thanks, and I'll see you in the next video.